Hello, this is Miss Moore, and today we're going to talk about entropy and Gibbs free energy. And today's essential question: what determines if a reaction is thermodynamically favorable? All right, so first thing to think about is what reactions actually occur. So let's go back and talk about enthalpy for a moment and thinking about exothermic or endothermic reactions. So intuitively, it might seem like all exothermic reactions would actually occur, right? So if you have a negative delta H, you would assume that the reaction would occur because it's has excess energy, right? You're releasing energy, so it seems like it should be spontaneous or it should occur naturally, I suppose. It also might seem that an endothermic reaction would not occur because you actually need to put energy in. So I don't mean that it wouldn't occur, but it wouldn't occur spontaneously. Okay, so in a situation where you have a positive delta H. Now, points 1 or 2, what I'm talking about is intuitively. This is what it would seem like would be true. So point 3, of course, the statements above, they're logical. It makes sense intuitively. But they are not necessarily true. There's more to the story. So when looking solely at enthalpy, a negative delta H or a exothermic reaction, we would predict that the reaction would be spontaneous. Okay, it would happen without extra effort. Where a endothermic reaction or a positive delta H we would think of as not spontaneous. That we would have to do something, add energy, for the reaction to happen. And again, this is if we're only talking about enthalpy. But like I just said, there's more to the story. So what's part 2? Part 2 is entropy. And entropy is a degree of disorder or dispersal of energy in a reaction. And it's actually, let's add a little bit to that, it's the degree of disorder or dispersal of matter and energy in a reaction. And I'm going to try to talk more about that. Not try to. I will talk a little bit more about that in a minute. So entropy is symbolized as an S. And we have a reaction here that looks very familiar. We have the change in entropy of the reaction equals the sum of the entropy of the products minus the sum of the entropy of the reactants. And you can find this entropy or delta S in our thermochemistry data table, which I have right here. We've used this same data table already to look at enthalpy, the delta H. And we also have this we also have here the entropy. Okay, same data table. All right, so back to this. Something I should point out is that these little degree looking signs means that we're talking about at standard temperature and pressure, or 273 K or 0 degrees Celsius and 1 ATM. Okay. All right. So an increase in entropy is assigned a positive value. So a positive change is an increase in entropy, where a decrease in entropy is assigned a negative value. So when we're talking solely about entropy, a positive delta S or an increase in entropy is the one that's more likely to be spontaneous. And a decrease in entropy or a negative delta S is not spontaneous. Okay, so I want to talk about why that would be, kind of give you a visual. I like to think about, okay, let's take my bedroom, for example, keeping in mind that entropy is the degree of disorder or dispersal of matter and energy. So let me think about my bedroom. You can think about your bedroom or your house or whatever. The degree of disorder in my bedroom, like dropping my clothes on the floor or, leaving stuff all over the bathroom sink or whatever, that was pretty spontaneous, right? Didn't take much effort to get there. An increase in disorder, easy to do, spontaneous. Now, to get it back in order again, to clean it all back up, to increase the order, not spontaneous. That took some effort. I had to go in there, pick everything up, put it away, hang up my clothes, whatever. Okay, so for entropy, an increase in entropy, a positive entropy, is spontaneous. It's easy to get disorder. It's the natural state of things. It takes effort for there to be less disorder. That would be a decrease in entropy, less disorder. That takes effort. That is not spontaneous. Let's move on and talk about entropy values. And what I mean by that are what kind of things affect entropy or state of disorder. So the state, whether it's liquid, so the state, I mean, is it liquid, solid, or gas? So liquid, solid, or gas. Or aqueous. The temperature, the number of particles, it could be the number of particles, it could be the moles of particles, and the volumes of gases are all important factors in entropy. So here's what we know. We know that solids have less entropy than liquids, which have less entropy in gas. Keeping in mind that entropy means entropy is degree of disorder. So it should make sense that solids, which are tightly bonded together with not a lot of movement, something we talked about during the gas laws unit, they're going to have less disorder than a gas, right? Which the particles can move very, very freely. Okay, so gases are going to have a much more positive change in entropy than a solid is much more likely to be more negative. Okay, entropy or degree of disorder of a small number of particles is less than entropy of a large number of similar particles. I mean, you can think about that too. Think about your room. If you don't have very much stuff in your room, it's easier to keep organized, right? Less entropy because there's more order. The more stuff you have, the more likely it is going to be disordered. Okay, so less particles means less entropy. More particles, more entropy. Okay, onward. Volume can, when we're talking about gases, volume can change entropy. So if gases have a smaller volume, there is less entropy than gases with a larger volume. There's more space to move in something with larger volume. The gases are going to be more spread out and more disordered. Okay. Absolute entropy increases with increasing temperature. So higher temperature equals more entropy or more disorder. And again, that should make sense. The molecules move more at higher temperatures. Entropy of more complex structures is greater than entropy of less complex structures. So, for example, so more complex structure would be something like C6H12 it's more complicated, right? Because you're going to have, why did I pick one quite so big? 1, 2, 3, 4, 5, 6. Something like that, right? Versus C2, no, let's just go CH4. Okay, so this has more entropy than does this one. Okay. Nope. Yeah, okay. So sorry, I scooted ahead. So let's now move on to practicing this. We're going to do it both mathematically and thinking through it. And here is our practice problem. And what we're going to do here is we're going to predict. We're not going to, you notice it says predict, not calculate. So let's talk about, just thinking about the things we've learned, predict whether the entry change, that doesn't even make sense. Let's try that again. How about enthalpy change of the system will be positive or negative? So I guess the first thing we talked about was state of matter. So let's look at what we have here. If we're talking about state of matter, we have a gas and a gas going to a liquid, right? So gases have more entropy. Sorry, let's try that. Oh. Hopefully one of you guys shouted out. I wrote enthalpy. This is entropy. Sorry about that. Okay, so gases have more entropy than liquids. So what is the change? When we're talking about change, we're talking about going from the reactants to the products. Okay, so going from gas to liquid, the delta S is likely going to be negative, right? We are decreasing our state of disorder or our entropy. Okay, which means it's less likely to be spontaneous. Let's see, what else could we talk about? Can't really talk about temperature. We could talk about number of particles. We have 2 here plus 1. So on this side, we have a total of 3 particles going to only 2 particles on this side, right? I'm looking here at the, that didn't work out very well. I'm looking at the coefficients. So we could be talking about single particles or moles. But looking at this, we also have a decrease in entropy, right? We're actually becoming more ordered or less disordered. Okay, let's see. What else did we talk about? You can't really talk about temperature, volumes. We can't really show in this problem. Number of particles and whether it's solid, liquid, or gas. Those are really the only 2 we could talk about here. I suppose we could sort of talk about complex structures, although in all honesty, none of these are very complex. But if we were to look at the complexity of the structures, let's say we have HHOO. So this structure here is slightly more complicated. So you might predict for this particular case that entropy is increasing, but the structures, none of them are very complicated. So we'll ignore that. Okay, so looking at, just predicting, it would look to us like delta S, or the change in entropy, is decreasing. It's becoming more ordered or less disordered. It's really, really important that you're able to predict delta S, positive or negative, looking at the reaction. However, it's possible you could have to do some calculations too, so I want to try that really quickly. So we're going to do a quick practice problem here. This time it says use the standard entropy values to calculate. So we are going to use calculations. The standard entropy change for the following reaction at 25 degrees Celsius. Okay, so remember that delta S equals, I didn't want that. Delta S equals the sum of the entropies of the products minus the sum of the entropies of the reactants. And so all we need to do here is your basic chug and plug. Plug and chug. So let's see, our products we'll do in orange. So we're going to look up HCl gas, and we know that there are two of them. So we're going to have 2 times, let's see, I put a little table here, HCl is right here, and we are looking for delta, we're looking for the S, so we're going to use 187 joules per K mole. So 187 joules per K mole minus our products, which I guess we'll do in yellow. No, not our products, sorry, our reactants. So we have H2, and we only have one of them. So H2 is here. And it's 131. 131 joules per K mole. Plus Cl2 gas, which is here, 223. Right, equals log delta S. All right, so we can plug those into our calculators and see what we get. All right, so if I did my calculations correctly, I ended up with 20 joules per K mole. And by the way, this here, these all should have been mole, not am. Okay, so that's how you do the calculations. You've done this before. Alrighty. So now let's talk about spontaneous reactions. A spontaneous reaction, also known as a reaction that is thermodynamically favorable. That's spontaneous or thermodynamically favorable, is a reaction that is likely to occur. Okay, so we've talked about two big factors that can contribute to the likelihood of a reaction being spontaneous. One is enthalpy, or delta H, and we talked about the fact that you would predict that an exothermic reaction would likely be favorable, or something with a negative delta H. The second is entropy, which is the disorder. Things that are more disorderly, increased disorder, is more likely to be spontaneous or thermodynamically favorable. So what we're looking for is something with a negative delta H and a positive delta S. That reaction is likely to be, though a reaction that has both of those is very, very likely to be favorable. So exothermic and disordered. Okay, so that brings us to Gibbs free energy. Gibbs free energy, which we symbolize as a delta G, is a measure of the likelihood of a spontaneous or thermodynamically favorable reaction. And a negative delta G indicates a spontaneous reaction. So negative delta G equals spontaneous. And we've got a couple of equations here. First one being one you've seen lots of times, just with a delta H or a delta S, and now a delta G. Delta G of a reaction equals the sum of the G of the products minus the sum of the G of the reactants. And I am not going to do a problem showing you how to do that, but I will point out that on your tables you have delta G numbers as well. Okay. This is the important one. If you know both delta H and delta S, so the enthalpy and the entropy, as well as the temperature in Kelvin, that's important, you can calculate the likelihood of a reaction occurring. You could also, by looking at the numbers, make a prediction. So this right here is really, really important. This is the big part of Gibbs free energy. So what I want to do, we could do calculations, but honestly, for both of these here, it's plug and chug. What I want to do is talk more about the thinking aspect. Okay, so here's this equation again. Remember that for the reaction to be spontaneous, we need a negative delta G. Okay, so if you think this through mathematically, an exothermic reaction, or if delta H is negative, right, and delta S is positive, so what you would think of, you would have a negative number, so some negative number minus some temperature times a positive number. Okay, so a minus, and this is going to end up being a negative, right? So a minus and a plus, a minus, or minus, we're going to end up with some big negative number, leading to a spontaneous reaction. Hopefully that makes sense. But let's change this up. Let's say delta H is now going to be positive. So we're going to have a positive delta H, which we would think of as, for the most part, that would be not spontaneous, right? Minus some temperature times, let's make delta S also not spontaneous, negative delta S. Okay, so now think of what we have. We have a positive, and then a negative times a negative equals another positive. Right? There's nothing we can do. This reaction is going to be not spontaneous. Okay, so when we have an endothermic reaction and a negative delta H, a negative delta S, meaning we've increased the order or decreased the disorder, we're going to have a not spontaneous reaction. Does that make sense? Okay, I'm going to erase this. I shouldn't have done that because I want to keep track of what we did. What did we just do right here? This was a positive delta H and a negative delta S. This is going to be not spontaneous, right? Okay, so let's try where, let's see, let's make our delta H still positive. So we have a positive delta H. So we would think of that as being not spontaneous. And then we have our positive delta. Our delta S is also going to be positive. Okay. We want our delta G to be negative. So we have minus, so we have a positive minus temperature times a positive. What number needs to be bigger for delta G to be negative? Do we need this part to be bigger or this part? We need this, we need the T delta S to be a bigger number, right? For that to happen, if our temperature, we had a high temperature, this would be a bigger number, right? So, what a mess I have here. I guess I'll put it up top here. If we have a positive delta H, which seems like non-spontaneous, and a positive delta S, which seems spontaneous, it could be spontaneous at a high temperature. Okay. Don't try to memorize that though. Think about why. We need, if this is a big number, the negative will be bigger, leading to a spontaneous reaction. Okay, one more. This time, we will make, our delta H will be a negative number, okay, which would make us think it's spontaneous. Have we done this? No. Okay, minus some temperature times, we're going to make delta S a negative number. Okay, so a negative times a negative equals a positive, right? We have a negative here. To get delta G to be negative, we need this thing here to be a small number. So we need the T needs to be small, meaning a low temperature. Because if delta S is negative, and we have this negative right here, negative times a negative equals a positive, so we need basically that to be a very, very insignificant size compared to the delta H. Let's get rid of this mess here and look at this situation again. So if we have a negative delta H, which we would think of as being not spontaneous, right? It's endothermic. But we have a positive delta S, which we think of as spontaneous because we're increasing a disorder. We can end up with a spontaneous reaction at low temperatures. So what you guys need to do is think through, I mean, you could memorize all these things I wrote down, but if I were you, I would not. Let's get rid of this stuff real quick. As you guys know, if you just memorize everything, you have a tendency, your brain has a tendency to go backwards halfway through, and that's never a good thing. So what you want to think of is that you want delta G to be negative, right? Then look at this part here. Okay, think about, do you need this to be a big number or a small number? That whole, the T delta S, to get a negative delta G. Okay, so you would look at H compared to T delta S. Decide, big or small, how do I get this thing to be negative? And then you can talk about a low or a high temperature. Okay. So you will have calculations on entropy and on Gibbs free energy or delta G. But that's the easy part. The harder part for both entropy and Gibbs free energy, delta G, is to the thinking part. Okay, so that's the part you want to focus on. And that's it for today. Have a good one.